Hello, so our project is about models for four image classifications. Motivations. So now when we talk about image classifications, neural networks seems to be the most popular method. Although it is proved to be quite effective, there is also a disadvantage of it. That is, one, it is time consuming and also is computationally expensive. In contrast, the traditional machine learning methods are much more time efficient. So inspired by this advantage, we want to investigate the performance of traditional machine learning methods on image classifications. And the algorithm we pick are shown in the slide. At the end, if the traditional method could also achieve a decent accuracy, it will be a much better option than the neural network.
Okay. Hi, I'm Wei Hang. I'm gonna introduce our data part. So basically, we use the data. The name is the fruit 360 on Kaggle, which is a commonly used data with many images of fruit and vegetables. So basically, the image size is 100 multiple 100 pixels. As we just want the binary classification and like 3 labels or 4 labels, we only select 6 pairs of fruit. So basically we select the pairs that with similar shape, with different shape, and with the same kind, but different color. Okay, and for the data preprocessing, we read the images as NumPy array and save them as a NumPy file. In the screenshot, you can say that, you can see that we created hash and train data for each pair of fruit. And for the independent variables, the shape is for each pictures. We have 100 multiple 100 pixels, and for each pixel we have 3 values, which is the RGB. And then for the labels, each picture have 1 label. And for the project workflow, we work on the GitHub repo. We save the algorithms as the functions in the Python files, and we run the experiments on Jupyter Notebook. So as you can see in the screenshot, we have multiple Jupyter notebooks and multiple Python files. So this is an example of our workflow. Basically, we create the functions in the Python file, and this function read experiment is the function for us to read the data. And then we import those functions in the Jupyter notebook. As you can see in the screenshot on the right, this is our complete import message, and we define lots of Python functions to multiple use. And for the performance metrics, we use both accuracy and the F1 score as metric. So those are the formulas for the 2 metric. And the first model we use is decision tree, which is commonly used supervised learning method for classification and regression. Its paper have limited space, so we didn't put this part to our paper, but we still want to use, still want to show our results. So this is the result of our original data set without PCA and grayscale. As you can see, the performance is relatively good. And this is the result after we applying the grayscale. And this is the result after we applying the PCA to 2 dimension. Next part.
Okay, this is Yunbo. So when we do the PCA implementation, for the eigen decomposition part, our covariance matrix is huge. It's 30,000 by 30,000. It takes a long time to run the algorithm. So we found a more efficient method, the sparse.linearalgebra.sh, which specializes in decomposing symmetric matrices. And because covariance matrices are inherently symmetric, we use this function to improve the runtime. Next page, please. Okay, so after we do the PCA, we apply the GMM clustering. The 2 graphs on the left are of 2 principal components, and on the right are of 3 principal components. We can tell in this example, the GMM clustering do a good job. It clearly separated 2 distributions. Next page, please. Yes, so this is another example where GMM failed to give a clear clustering revealing the real distributions, probably because the 2 distributions are not Gaussian distributed, which we can tell from the 3D graphs on the right. next part.
Hi, my name is Jiaxuan, and I want to introduce my part, which is using the KNN algorithm. KNN is a simple supervised classification algorithm that we can use to predict label of this data point. Simply speaking, it includes the following 3 steps. First, calculating distance from between data points and training data, and then pick the K points that are closest and predict label for this data point according to a majority vote. Next page. Before I start the classification on our trials, I want to make sure that I'm using the best K parameter. I randomly picked a trial and tried K values from 1 to 10. As it is shown, K parameters ranging from 1 to 2 did the best work. Next page. For each trial, fit-skip-learn with X-train, Y-train, and predict Y values using the KNN we fit above with X text and output the predicted Y values. Lastly, define it in the function so we can use it anytime. Next page. After using the plot function that Wei Hong wrote in his part, we got the following results. We got very good results in all trials except trial 2. All other trials got accuracy of 100%. Next page. Then we applied PCA. Here are the results. We can tell that the accuracies are lowered after using PCA. 2 out of 5 trials still got 100% accuracy, but trial 2 got lower than 90%. And the 5th trial is classification of 3 different fruits, and the accuracy became the lowest. Next page. The decision boundary plot also tells the same thing. The plots of trial 2 and 5 are quite messy compared to all the other trials. Next page.
So lastly, we are going to talking about the supported vector machines. So a supported vector machine is an algorithm that classifies objects through finding an optimal hyperplane between classes. As depicted by the picture here, the hyperplane could be represented as W times X minus B. In this equation, W denotes the weight and B denotes the bias. The hyperplane is estimated in such a way that it could be as far as possible from the data points. And in this study, the kernel we used was the RBF kernel, and the regularization parameter was set as 1.0. So let's look at the result. So first, I apply SVM to the most original data, no PCA and no grayscale. And it turns out that SVM was performed quite excellent, that it achieved 100% accuracy for all experiments. And then I tried with PCA and projecting the data with only 2 PC components. It seems like it's still performing with a decent accuracy, that it achieved 100% for almost all of the trial, except for 2 and 5. And 2 and the drop accuracy on trial 2 and 5 is actually consistent with the KNN result as well. And lastly, just to explore the boundary of SVM, I also tried with the grayscale data. And it is still performing quite well, that it achieved 100% on almost all of the experiments except for experiment 2. So in summary, the accuracy order is SVM performs the best, and then to KNN, and to GMM, which is similar to the decision tree. And one interesting observation we have in this study is the dimensional reduction method actually lowers the accuracy level. This is actually out of our expectation, because usually it could actually increase the accuracy level. And one possible reason is because this dataset is specifically designed for image classification, so there's probably not a lot of irrelevant information. And the second observation we have is the classifier seems like it outperforms the GMM. And one possible reason is because GMM is a generative model, while the classifiers are discriminative model. The discriminative model only considers the distance between data points rather than trying to model the distribution of the data. When we are dealing with a complex data, this is probably a better approach. And also, if the data wasn't Gaussian distributed, then GMM is probably not the best approach. In terms of the future work, we would like to play with multi-class classification to mimic the real-life situations. And also, we will also like to play with a different set of data in order to validate our results, to show that it's not only to this specific data set we have.